I just want to do the briefest of overviews into finding relative extrema for functions of two variables. It will be very brief and not very deep. The technique that we learned earlier about setting the derivative equal to 0 to find the critical numbers of a function of one variable can extend to functions of two variables, and it's really fairly simple. To find the critical points for a function of two variables, compute the partial with respect to x, set it equal to 0, partial y, set it equal to 0, and that result will give you the critical points. Now, it may turn out that you get a set of two equations and two unknowns to be solved to get through this, and sometimes it's much simpler than that, and I want to illustrate that with a couple of examples. Suppose I have the function f of x comma y equal x squared plus y squared plus 4x minus 6y plus 5. Now, to do what I said just above, I need to compute the two partial derivatives, partial with respect to x, partial with respect to y. Let's just start off with partial with respect to x. Now remember, when I do that, I'm holding y constant. And going back to what we learned previously, if I scan through that function, the second term y squared is being held constant. If y is constant, then y squared is constant. And the fourth term, the minus 6y, is also being held constant. There are no x's in either of those. So both of those are just numbers. We just think of them as numbers. So the partial with respect to x is just the derivative of the first term, which is 2x. The derivative of the second term, which since it's a constant is 0. The derivative of the third term, derivative of 4x is 4. The fifth term being a constant, we get 0, and the sixth term is certainly a constant, so its derivative is 0. So when all is said and done, the partial with respect to x is simply 2x plus 4. Now we've got to do the same thing with the partial with respect to y. If I write this back down again, the function, and emphasize that when I'm doing the derivative with respect to y, that I'm holding x constant, then the first and the third terms are constant. So when I take the derivative with respect to y, I get 0 plus the derivative of y squared, which is 2y, plus the derivative of that constant, 0. The derivative of negative 6y is negative 6, and the derivative of 5 is 0. So I end up with the partial with respect to y being 2y minus 6. Then I want to set those two things equal to 0. Well, when I set 2x plus 4 equals 0 and 2y minus 6 equal to 0, and just go through the simple algebra, I get x equal minus 2 and I get y equal 3. So the point minus 2 comma 3 is a critical point. In the simplest cases, this is very simple. Let's do another one. Find the critical points. The function's slightly more complicated, but not a whole lot. But the process is the same. I want to take the partial with respect to x and the partial with respect to y. So I'm going to do the partial with respect to x first. I want to look at that function and think of all the y's as constants. Now notice I flipped in the second term, I put the y first so I could combine it with a 6 because both y and 6 are constants. So 6y is just one big en. I'm a number. And in the third term, there is no x at all, so everything's a constant. In the fourth term, there are no x's, so everything's a constant. And of course, 1 is a constant. So that derivative is very easy. I get x squared. Remember, the derivative of a number times x is just the number, and 6y is playing the role of a number. And everything else has a derivative of 0. So the partial with respect to x is 2x plus 6y. Now I'm going to do it with respect to y. Now I have to remember that I'm holding x constant. So the first term and the 6x in the second term are both ens. They're both numbers. So their derivatives are going to be thought of in terms of that. There are no x's anywhere else, so all the other terms will have normal derivatives. Going back through there now, the derivative of x squared will be 0 because it's just a number. The derivative of 6x, which is a number, times y is just a number. That'd be 6x. The rest of them are just ordinary derivatives. The derivative of 10y squared is 20y. The derivative of minus 2y is minus 2. And the derivative of 1 is 0. So when all is said and done, we get the partial with respect to y is 6x plus 20y minus 2. What do you do with that? You set them equal to 0. So I take the first derivative with respect to x, set it equal to 0. Take the derivative with respect to y, set it equal to 0. That's a system of two equations and two unknowns. Now you can solve that by elimination, you can solve it by substitution. I chose to do it by substitution here, but there's nothing wrong with doing it by elimination. This is basic algebra that you've learned before, so however you choose to do it. I decided to take the partial with respect to x and just solve for x. It was very easy to do. So x is equal to minus 3y. And then if I take that second equation and plug the minus 3y in for x, multiply that out, I get negative 18y plus 20y. I move the negative 2 to the other side and make it positive 2. Negative 18y plus 20y is just 2y, so I know that y is 1. Now I know that x is negative 3 times whatever y is, so now that I know y is 1, I can figure out that x must be negative 3. And like I said, you could have solved this by elimination if you had rather. It'd work either way. So the point negative 3 comma 1 is a critical point. You'll recall that when we were using functions of a single variable and we found the derivative set equal to 0 to get our critical number, we had a test to decide if that critical number was a max or min. There's a similar test when we're working with functions of two variables. I like to call it the d-test. Some people call it the second partials test. But in either case, you sort of need a corresponding picture in your mind of a function of two variables. You have a surface instead of a two-dimensional graph. So you can see, just looking at this picture, you can have maxes and mins, and you can have critical values where it's sort of equivalent to us finding a value that wasn't a max or a min. It's called a saddle point. But in your mind, you sort of have a picture of a surface, not a 2D picture. Nevertheless, this d-test will help us locate relative maxes, relative mins, and the places that turn out to not be either, called saddle points. How do you do it? I actually incorporated the step of finding the critical points into the d-test. I guess if you're going to be picky about it, you've already found your critical points before you go to the d-test. But just to give us a one-stop shopping, I just put that step into the d-test as well. In any case, you're going to find the critical points, whether you consider it a part of the d-test or not, by setting the first partial with respect to x and y equal to 0. Then you're going to need your second partials, and actually you only need 3 of them. You need the xx second partial, you need the yy second partial, and you need one of the cross partials. You can either do xy or yx. It turns out for the functions we'll be dealing with, those two cross partials are the same anyway. So take the one you like best. And then you compute this quantity called d. And d is the second partial with respect to x, the xx second partial, multiplied by the yy second partial, minus the square of the cross partial xy. Now technically, you need to plug in your critical point into that d formula to calculate, but lots of times the second partials come out to be just constants, which means there's nothing to plug into. So sometimes it's, even though I'm saying plug in the critical values, sometimes there's really nothing to plug in or nothing useful to plug in. So you'll see that when we go through the examples themselves. But in any case, once you get the value of that funny looking expression d, you have to interpret it, and here's how you interpret it. And this is not as bad as it's going to seem. You'll see that when we actually get to the examples. But I want to go ahead and get through the test before I try to convince you that this is not as bad as it looks in the beginning. You have to interpret that result. If d is positive, if you do the calculation for the value of that quantity d, if it comes out positive, then you have to look at the xx second partial. If it's also positive, you found a relative minimum. If d is positive, but that xx second partial is negative, you found a relative maximum. If d is negative, then you found a saddle point. If d happens to be exactly 0, the test fails, and you can't tell what you've got there by using the d-test. There are other alternatives which we won't discuss, but the d-test itself fails. It's very similar to the second derivative test in that it can fail. Now I want to convince you that this is not as bad as it looks by going through a couple of examples. Suppose we take this function, two variables x and y. It's x squared plus 6xy plus 10y squared minus 2y plus 1 and show how the d-test works. I'll pop it back up here and go through the steps. The first thing we want to do is find the critical points. So how do you do that? Well, we just did it. That's exactly the same function we just worked. I wanted to sort of condense our work here, so I just chose the exact same example we did a minute ago. So we already did that, and I'll pull the important stuff from the work we just did. So we did that already. So now we can go to step 2. Step 2 says to compute the second partials, at least 3 of the 4 of them. In order to get the second partials, you have to have the first partials. Well, luckily, we already did the first partials back in step 1, so I'll just write them down again. How do you take the partial of x with respect to x? In other words, the second partial xx, you hold y constant. So the derivative of 2x is just 2. Well, if y is constant, then 6y is constant, so 6y is just a number and its derivative is 0. Then you do the partial xy. That means you go to the partial of x, the one that's right above there, but this time you let y be the variable. So this time y is the variable, but x is just a number. Well, if x is a number, 2x is a number. So the derivative of 2x is 0, and the derivative of 6y is just 6. And then finally you go over to the partial with respect to y and do it with respect to y again. That means that you're holding x constant. Yes, that means you're holding x constant, so the 6x is just a number. And the negative 2 is just a number, so all you really have that's not 0 is the derivative of 20y, which is 20. Now, if you're still having trouble doing partial derivatives, you need to pause this and go back and correct that problem before you come back here. I'm assuming now you've got these basics of doing the simple partial derivatives down. If you don't, you need to correct that. In any case, we've got the 3 partials that we need to, the second partials that we need to compute d. So now we're ready to go to step 3, which is to find the value of d. So d is that funny looking expression. It's the second partial with respect to x times the second partial with respect to y minus that cross partial xy, that quantity squared. Technically, you're supposed to plug in the critical values for a and b, and the thing looks like that. I will say, though, when the second partials are just numbers, you really don't even have to do that step because the values of x and y don't even come into play if the second partials are just numbers. So I put that second step in there for completeness because sometimes you need it. But when the second partials are just numbers, you don't need it, and you can just skip that step, or you can do it. It doesn't matter. Either way, you're going to plug in a 2 for the second partial with respect to x, and you're going to plug in a 20 for the second partial with respect to y, and then you're going to plug in the 6 here and square it. So the calculation of d is really pretty simple. So you've got 2 times 20 is 40, and 40 minus 6 squared is 40 minus 36. So actually you found out now that d is equal to 4. And that's step 3. The last step is the interpretation step. You just look at the value of d, whether it's positive or negative, and if it's positive, you look at the second partial with respect to x, the xx one. So if you look back at this, to interpret d is positive. D came out to be 4. That's a positive value. If d is positive, then you've also got to look at the xx second partial and see if it's positive or not. Well, the xx partial is positive. 2 is a positive number. So that's the case that I've circled up there where d is positive and the second partial xx is also positive. If you find that that's true, then you found a relative minimum. So that critical point that we found, that is a relative minimum. So once you practice this, this is not that difficult. You've got to be really careful getting your partial derivatives. You've got to write the formula d down correctly, and then be very careful with the arithmetic. But the process is not difficult. If you're having trouble with this, go back and do it again and again until you can flow through this without making any mistakes.